Hey, what's up, guys? It's Shane, and I'm just sort of going to be going over our code. I already did this before, but at that point, our code is so outdated. Like that was like a few days ago, and our code is already outdated because we've made a lot of progress, especially with the colors and stuff. So I was just sort of thinking I was gonna go through like almost every line of code, kind of. It's a little bit ridiculous to do that because I don't even understand every single line and exactly what it does. But I was thinking I could just sort of go through what makes the output possible and really like what we have and like what's going on with it. So I'm going to start with the driver class because the driver class is really what gets everything going. It's a script. It's not a class, it's a script. And it's different from all of these other classes. It's sort of like a built-in driver class in Java almost. Like it's responsible, it's where all the objects are created. It's where the program really moves along, where all the methods are called from, and where everything sort of goes back to it. All goes back to the driver. So yeah, I'm sort of just gonna be going through the driver. I actually, if you guys notice, I shortened it quite a bit. It used to be like 250 lines, but I made it more efficient, or at least tried to. And yeah, so I'm just gonna go through this whole thing because it will take us everywhere we have to go. So let's start at the top. So this clear all function, basically it clears every single value out of a variable that was already defined. CLC, it just clears the command window, and then close all, that closes any files you have open, any figures you have open. It closes down like videos, images. It's just great for that. So it's always good to put these at the top because it starts you off with a clean slate. So the code from this endpoint all the way up to folder is the code used to manually get the file that you're looking for. There's actually an easier way to do this, but this is just sort of the, I guess, more professional way, I want to say, the better way of doing it. So what happens is that there's this folder variable, and it's equal to the folder that you want to look into. So if you can tell, it's C users Shane desktop test, and that's actually the folder we're in right now. And then the file desired is just that. It's the file that you want. And this full path concatenates these two and puts this wallpaper.png right after test. And if you can tell, wallpaper.png is within test, as you can see right here. And so essentially what it does is it checks for if this full path is an actual existing file, and obviously it is in our case, but if it isn't, a little error message pops up and just tells you, hey, your file isn't working. And I'm sure we have dealt with that before, guys, if you don't remember. And yeah, it just prints out a little warning message. So let's go down to line 17. So color line x start equals 0. So what that is it's a variable that establishes that we want the color line that we're gonna create to start at the origin at x equals 0. And obviously it's not gonna always stay at x equals 0. In fact, in the color line class it will change based on how many frames you're looking at. However, we always want it to at least start at x equals 0 because we want to put the lines side by side, so obviously it won't always be 0. Now the total frames will always at least be 1. If we've gotten to this point, we have an image or we have a video, so obviously we're at least going to be looking at 1 frame. So we start the total frames at 1, however obviously that may increment up. So is an image and is a video are both Boolean variables, and essentially what they are is, it's pretty self-explanatory. If you're dealing with a JPEG or a PNG, then it's an image. If you're dealing with an AVI or an MP4, then you're looking at a video. And it's important to note that as for right now, we can really only work with PNGs and JPEGs. We might be able to work with other file types that are encoded in a similar way. However, I haven't really looked into it. I've looked at the .tiff files, and a while ago I actually got them working, like last week, but the PNG and the JPEG files stopped working, and to get all three of them to work would just be a lot of if statements and a lot of hair pulling. So I think it's just worth it to just stick with the JPEG and PNG anyway, because it's easier to grab the RGB values. Now, it's funny that I mentioned that, because then with videos, it seems like you can use whatever video format you want as long as the video is in an RGB format. Because of the way that MATLAB grabs each individual frame of a video, as long as it has an RGB channel, it's really easy to access the RGB values. So I think we can use anything like an AVI, MP4, .mov, .mpeg, anything really. It doesn't even matter. Like, so it's interesting that we're kind of restricted on the images, but not so much on the video. So coming down here, the color names and the color values. So these are probably the two most important arrays that we have within this program. It basically establishes all the colors that we want to look at. It establishes their name and their RGB value, and these are actually parallel arrays. If you can tell, 255, 255, 255 is equal to white, and dark red is equal to this. There's probably a more efficient way to do this, but I'm just going to keep it like that for now because it's working out well. And these are probably the most two important arrays, because if I were to delete this, the entire code would literally break. So then we come down here, and we have to recognize that at this point we haven't done anything to the images. We haven't even assigned, or the video or the image, we haven't even assigned a variable to the image yet. So we're still sort of starting out here. We're starting to get like everything going. So the first frame, obviously we're gonna be on our first frame if we haven't even looped through the video yet, and we're gonna be on our first frame if it's an image anyway. So we just set this to true, and this is an important variable. It might seem a bit redundant right now, but it actually comes into play a little bit later, and we do need it. So frame count. This is basically just starting us off at 1, and it will increment every time we loop through a video, and it will stay at 1 in an image. However, obviously, again, we're always at least looking at 1. And it's the same thing with number of frames displayed. This is always equal to 1 as well. And this is a little bit different from the frame count, because the number of frames displayed is the number of frames that we will be showing in our program. So we can actually like skip around the frames, which I will show later with a different variable. But this is mainly important because the number of frames displayed also determines the number of lines, the color variation lines that we have to draw. So it's important to know that number, and you'll see why. Trust me. So these three are a little bit confusing. These three lines of code: subplot column, subplot line, and subplot 3D. So basically what happens is when you actually display the plots onto a figure, right, it basically puts stuff into rows and columns. So let's say that you have a subplot. Let's come down here. Let's say this is 4, this is 2, and that's 1. That means you have 4 rows, 2 columns, and you're putting it in the first row and the first column. So the way we want to display our images is different from the way we want to display our videos. There's a little bit more associated with the videos. So what this does is it establishes where we want certain things, like the color variation lines and the 3D graphs, for an image. However, as you can see here, when we're looking at a video with this if statement, we will want that to be a little bit different. Instead of being in the 5th and 6th plot, we'll want the 3D graphs to be in the 10th and the 11th plot. It's a little hard to explain without you guys seeing it, but I think you guys get it. Now, if it is a video, so let's pretend we are looking at a video, then we establish an object that represents that video and reads that video. This is important because this is basically the line that allows us to use a video. And obviously it's an RGB, we take it as an RGB video. So this is the method to get some of the info from the video object. I know it's a little bit ridiculous. It doesn't really give us much. I think it gives us like the frame rate and the resolution and like stuff like that. But the frame rate is important because it will tell us how many total frames there are in the video once we get the duration. And we get the duration down here from the video reader, and then getting and just looking at the file desired, like looking at the video. This gives us more info, essentially. I don't really know exactly how it works, but it gives us more info, and that's how we get the duration. That's the most important part. So obviously the frames per second times the number of seconds that it runs for will give us the total number of frames, and I just round it off, and it seems to work. I was thinking about flooring it or rounding it up all the time, but it works when I just round it either way. So now remember, we're still looking at if it's a video here. So what this line of code does, this step video object, is it moves through each frame of the video. So technically right now, before this line, we're on the 0th frame. We're not on one. However, when we do this line of code, it brings us to the first frame. So now we're on the very first frame, and this is important. This variable is going to keep changing because we need to step through the video depending on how many frames there are. And then we come down to the skippable frames. So remember when I was talking about how we can sort of skip around the video, we don't have to go frame by frame? Well, this is the variable that lets that happen. Essentially, there's a for loop way down here that uses this. But basically what happens is if you set this to say 1, then you're just going to go through every single frame. 1, 2, 3, 4, 5, 6, 7, you know. But if you set this to something like 50 here, then you'll start at the first frame, then go to the 51st frame, then go to the 101st frame. So you skip ahead 50 frames every time. And it's great because MATLAB is really slow at showing each frame of a video. Trust me, like super slow. Like a 30-second video can take an hour to go through. It's a little bit crazy. And now this number of frames displayed, so that's determined by taking the total number of frames. So say you have 500 frames and then you want to skip 50 of them. Well, that means that you're going to be doing 10 frames. That you're going to be displaying 10 frames because that's just how math works. So that means if you're displaying 10 frames, then you have to draw 10 lines, 10 color variation lines. And I just round this up all the time because for whatever reason it wasn't working otherwise when I rounded it down or just rounded it based on just the basic round function. So I'm using the ceiling function here. Okay, so oh, that was weird. I don't know. Just thought I heard something. Okay. Anyway. Alright, that was weird. Okay. Anyway, this for loop right here, what it does is it goes through basically every frame that we are actually going to display. So this will always be 1 when we're just looking at an image, which if you remember right, we established it was 1 up here, and in the if statement for is a video, if it is a video, it will change based on its total frames and the skippable frames. So this will always be 1 if it's an image, so it'll only go through the loop once, obviously. So the first frame here is a little bit important. It's really not that important. This is sort of a pet peeve of mine. I just always wanted to start at 0, and otherwise, if it's going through the second loop, obviously I want the X start to move over to the right once because the line that we're drawing is 1x thick. So if we move over the X start 1 over, then it will be exactly to the right of the line previous. So let me see if I'm explaining this right. So if you have the first frame, it'll be from 0 to 1, x equals 0 to x equals 1. And then the second frame, the color line will be from x equals 1 to x equals 2, if you see what I mean. So now we come down here, and this is where it gets a little bit weird. So if it is an image, then we create an object that holds this image based on the full path, which is just C, users, Shane, desktop, test, and then wallpaper.png. But if it's a video, it's a little bit different, because remember, we already got the frame, we already got the very first frame of the video. Now though, the problem with this frame of the video is that it's a double, and that's a problem when we're trying to work with RGB values. We have to convert it to an unsigned integer that goes up to the 2 to the 8th power, which by the way is 0 to 255, which is the RGB values. So that's why we kind of need to do that. And yeah, so it works like that. However, this will come to bite us in the butt later, but I'll explain that because I figured that out tonight, and that was not fun figuring out. Anyway, so then the initial image and the manipulated image are equal to this step, this frame now that it's RGB compatible, I suppose. And it's also important to note that while the initial image and the manipulated image are exactly the same right now, there's no difference between them. They both look like this for right now. They're literally just duplicates of each other. However, we're going to be changing this manipulated image. So basically what we do is we create an object that is manipulatable. I know that's a weird word, but we can manipulate it. And what we do is we send our image, the duplicated image, to the constructor of this image manipulation class. And it assigns a local variable to that image, basically, is what happens. And this is important because then it establishes an object that it will return later within the manipulate function. So that's what we do right away. So the manipulated image final is the actual object that contains the manipulated image. So we take the manipulatable object and we manipulate it with the manipulate method within the image manipulation class. So this is the manipulate method, and it's a little weird, and I don't completely understand it, but this is basically what happens. We create a color structure different from RGB, and it's called LAB, and basically you can change the luminosity, the red-green axis, and the blue-yellow axis. So I create another object that essentially is a copy of our initial object, our initial image. However, it went from RGB to now LAB, all right? And then what we do is we create 3 different arrays. One that holds all of the luminosity values of the image, one that holds all the red, green, and one that holds all the blue, yellow. And what we do is we change those values. So we change the luminosity, which is essentially the brightness. So the brightness goes from 0 to 100. So basically, the brighter your image initially was, the darker it will be now. So if your image was all white, it's going to be literally all black. We also changed the red-green axis, which essentially is basically switching the red and green colors. So a red turns green, green turns red. It's a little bit more complicated than that, but that's basically what happens. So now this object allows us, it basically combines these new the new luminosity value, the new red-green value, and the old blue-yellow, because we did nothing with that. It combines it, and this will allow us to to go back to the RGB color structure. So this makes a color structure that can switch from LAB to RGB, and then we apply that to a local variable called imageObject.manipulated_image_final. And this is probably the most important part, is this next line of code. So the actual object that we created with the constructor will be equal to this final manipulated image in RGB form. As you can see, we switched it to RGB form here. And it will return this image. Now this is important because it allows it to go back to the driver class and now be equal to this manipulated image final. So now we can see the manipulated image final within the driver class or driver script and use it. And this is the manipulated image. If you can tell, it was initially black here, but since we changed the luminosity, it's sort of grayish now, which is, you know, pretty cool. Yeah, so after we do all that, we get the image and the manipulated image. What we do is we send both of them down to the color proportions class, and this is the class that is responsible for determining the color of each pixel of the images, which is pretty crazy, and this is probably our flimsiest class that is likely to change in the future at some point. But basically what happens is we create an object that sends the image and the color names, if you remember, these names, to the color proportions constructor, and it sets the local variables there equal to those so we can use them within this class. And then what we do is we create an array that will be equal to this object, but with the proportions method tacked onto it after the proportions method is performed on it. So if we go over the color proportions and see what happens in the proportions method, this is pretty cool. So we establish what the total pixels are, and we're gonna loop through every single one of them. So at first it's 0, however it increments every single time we go through 1 pixel. We create this local variable called color proportions, and it basically creates an array that will hold all of the proportions of all 32 colors we have. And we set them to 0 at first, because we're gonna again count every single pixel if it's white or if it's black, and it will go up by 1. So we want it to all start out at 0. So this is where it gets a little bit interesting and kind of hard to follow. So again, JPEGs and PNGs are really, really easy to get the RGB values for. So essentially what you do is you literally just do this. You get the image and you get the third column of the image, basically. The information of the image, and you take the third column or the third row or something. I'm not really sure how it works, but this is essentially equal to the red values of the entire image. This is all of the red values in this red array. Same thing with the green array, same thing with the blue array. Now what I'm doing here is I'm reshaping it. So I'm sure you guys know what arrays look like. Now when you do this, the arrays look like a mess. They're just unorganized and stuff. But when you reshape it, what I do is I create a bunch of rows, in fact as many rows as there are pixels, and just one column. So that is just literally just like a long line of values. And then what I do is for all pixels, I put them directly next to each other. So there's 3 columns now. The first column is the red channel, the second column is the green channel, and the third channel is the third column is the blue channel. And the first row is the first pixel, the second row is the second pixel, and the third, and so on and so forth. And that's how it works. So this is how we get the row and the column. It's basically the row is equal to the height, the column is equal to the width, and the column is always 3 because there's 3 channels, there's R, G, and B, and the row is equal to the number of the pixels. That's just how it works out because of the way I resized this. So we loop through that. We loop through every single R, G, and B value. So we loop through a pixel 3 times to get its R value, its G value, and its B value. And this was where I was talking about how switching to a double to an unsigned integer can screw you over. Because the problem is that while the values go from 0 to 255 and they are real numbers, the problem is that if they're an unsigned integer type, they can't go below 0. And in a little bit, I'll show you how that can really screw you over. So, however, when you convert them to doubles, they can go basically anywhere. They can go -2 million to +2 million, all that stuff. So basically it grabs the R value of 1 pixel, then the G value of 1 pixel, then the B value of 1 pixel. and then it comes down here and it looks at the R, the G, and the B, and it decides, well, based on those values, what color is this? So if they're both above 224, all three of them are above 224, then it's white. So let's go over here and sort of look at this. So 224, 224, 224 actually looks kind of gray, doesn't it? It's kind of white, but it's kind of gray. Well, you know what? That's sort of true, but at the same time, like it's basically white. We can increase this, we can change this up if we want, we can play around with these numbers. It's really not that big of a deal if we're a little bit off, but I think that's a good point to start. Now, then it looks, okay, it decides it's not white. Well, is it black? So that's if the R, the G, and the B are all lower than 51. So if we look at 50, then 50, then 50, I'd say we can all agree that's pretty black. So if all of them are at least under 50, then it's going to be assigned black. And this, we're coming up to the point where this is where having it as an unsigned integer could screw you over so hard. So here you do the grays, and I don't know if you guys know this, but to get gray, generally the RGB values are pretty much exactly the same. So it's like 150, 150, 150, and that's like pretty gray right there. So what I did to determine if it was gray or not was I said, okay, if the absolute value of R minus G, G minus B, and R minus B is less than 3, then it must be gray, because think about it. If all of those are true, if all of the absolute values when they subtract them are less than 3, like for example, this would make that statement true. 148, 145, 146. Like that is pretty gray. You know what I mean? Whereas something like this wouldn't actually be considered gray. However, I might change that up a bit now. But what was happening was that these values, since they were unsigned integer values, it would just always go to 0. So for example, let's say R was 3 and G was 67. Well, 3 minus 67 is negative 64, right? So the absolute value of negative 64 is obviously greater than 3. But what was happening was it was doing negative 3 minus 64 equals 0, because an unsigned integer can't go below 0. So this was nearly always equaling 0, and it was always less than 3. So then it would assign it gray even though it wasn't gray. And this like confused the hell out of me. It was like this for a while. It's been like that for like a month, where it was a mistake like that. That's why gray was popping up all the time, even when we were certain that gray wasn't really a color that was in the image. And it's also important to note that like the way I'm doing each color is I'm doing white, then black, then dark gray, gray, light gray, dark red, red, light red, dark orange. You know, it's like a pattern of dark, then regular, then light. And the way I'm determining that is basically brightness is based on the total of the R, G, and B values. So the greater they are, the sum of them are, the brighter the image is going to be. You can see that here, 204, 229, 255. That's a pretty bright image. Whereas if you go up here, 25, 51, those are low values. That's a pretty dark image. Pretty self-explanatory. It's pretty easy to see how that works. And that's basically how it does it for every single one. And it actually works for, I'm going to delete this because that was just to debug it. It actually works so that every single color is assigned to a pixel, or every single pixel is assigned to a color, and it actually works quite well now that I fixed the gray issue. So what happens here is that this color props array is of size 32, and it contains the total number. It contains the total number of each color in there. So let's say there was 5 pixels that were white. Well, then the white element is 5. But we don't exactly want that. We want it to be a proportion or a percentage. So what we do is we divide it by the total number of pixels and multiply it by 100. So say there's 50 white pixels out of 100 pixels. Well, 50 divided by 100 equals 1/2 times 100 equals 50. Okay, that was an awful example. All right, let's say it's 500. Let's say you have 400 white pixels and 500 regular or 500 total pixels. Well, 400 divided by 500 equals 0.8. Then times 100. Well, that's 8, or yeah, then that's 80. So therefore, 80% of the image is white. So the color props, the sum of every single element in the color props will never be over 100 and never under 100. It will always be 100. That's how it works, and that's the only way it'll work properly. And again, this is probably the most important part: is you set the object that you created in the constructor equal to that array that contains all the percentages, and then you return it back to the driver script so that you can use it again within the driver. And that's what this initial props equals. This initial props is the same exact thing as this color props. Literally carbon copy, we just transferred it between classes. So this was just to debug to see that it's actually going to 100, which if we scroll up, we'll see that it actually is. It's equal to 100, which is great. That means it's working. We do the same exact thing to the manipulated image. So we get the color of each pixel for this image, and we get the color of each pixel for this image. And obviously they're different colors for some of the pixels. Sorry. So then we come down here and we create the bar graphs for both the original and the manipulated graph. However, we don't draw them yet. We do that towards the very end. Essentially, what happens is that we create these bar graphs. We give them the proportions of the percentages of each color. We give them the names and the values. We give them the names so that we can label the axes, and we give them the color values so that each color of the individual bar can be changed. So for example, if we look over here, we'll see that the black is equal to, say, 40-ish%, right? That means that, or it's equal to 40. That means that there was around 40% of the image was black, and it's important. And you can see the little label here. It's black, and we changed the color black to black. Like, that's what this color names and the color values. That's why it's useful. Then obviously we give it a title. We label the axes, all that good stuff. This is the width of the bar. So the width of the bar is literally just 1. It's really not that hard to see. It's just 1, and that way they line up directly next to each other, and it's just important to keep it that way. Also, this is the color variation line that I was talking about. Like, it literally stacks the proportions on top of one another. So obviously this is a little bit white. You can see some white in there, but it's not all that white, and I'll come back to this later, but this is essentially what the color variation line looks like, and we'll come back to that. And it's also important to see the difference graph object here. So what happens is that it takes the initial the proportion of the first original image, and it subtracts that color from the proportion of that color from the manipulated image. So for example, let's say that the first image was 80% white, but then the manipulated image is 20% white. Then the difference graph will show a difference of 60%, and it will show it right over here. So as you can see, this was about that's about 20-ish, and this is about 40. So obviously then the difference graph is going to be around 20 as well. So that's just sort of how the difference graph works. It's really simple. And here we actually create the difference graph object. This is just the array of the proportions, basically. So now this is where we create the color line for the manipulated image and the original one. However, I want to sort of go through the bar graphs class first. This is pretty boring and simple, just like this video. Basically, we feed it, the data. We already went through all this. So we get the rows and the columns based on the number of color names that are in there. So there's 32 names, and the number of rows should be, I believe, 1, and the number of columns should be 32, or the other way around, I'm not sure. But basically what happens is we're able to plot that data onto the graph. And it's important that we get those rows and columns, mainly because, where is it? There it is. Mainly because the X limit will need to be the number of colors plus 1. So that we know that there will be, say there are 32 colors here, we need at least 32 ticks on the x-axis. So that's why it's important to get the number of, basically the number of colors that you're working with. And then here we just set the X label and the Y label. This is a little bit complicated. Like, it's just changing the fonts, and it was sort of tedious to do because there wasn't an easy way to do it in MATLAB. Not very exciting. And then we set the background here to like a light blue because it just looks a little bit better. And here's where we actually change the color of every individual bar. So every bar is actually the same color when you make the graph. It's like this sort of lightish turquoise color. It's a little weird. And what this color does is it changes the color of every bar based on the color values that array that you sent over. So this array that we sent over, this color values array, is responsible for changing the colors of the bar graph. So say the first color, the first bar is the white. It represents the white proportion. Obviously we want it to be white. So then we just send over the 255, 255, 255. We use the very first element for the very first bar of the bar graph, and boom, now it's white, as we can see. Which, well, no, we can't. But the black one's better. The black one's a little bit better at showing that it changes, which is and black's the very last bar, obviously. So yeah, that's the bar graph class. So now we go to the color lines. And the color lines, again, the original line, the manipulated line, they look like this, the final version. I think they're pretty accurate, especially after the whole gray fiasco. They seem to be pretty accurate. I don't know. They're not exactly the most precise, but they're pretty precise in my honest opinion. This is pretty good. There's a lot of blue. There's quite a bit of green. And, you know, there's some yellow thrown in there and gray and all that. So I think they look pretty good. But basically what happens is we send them over the proportions because obviously they need that in order to draw the rectangles on top of one another. And then the color line X start. So this is most important for videos. So it determines basically how far away each line will be plotted from the other, since they're plotted right next to each other. I sort of already explained what that means. This is just basically the number of lines that we're going to draw, the number of frames displayed, and the color values, again, is the actual RGB values of each color, which, of course, is important. So let's go over to the color line, and this class is pretty straightforward in a way. Essentially what happens is, I'm not really going to describe the code here, I'll just sort of describe what goes on. So let's say, so obviously you have to start at y equals 0 and you have to get to y equals 100 because the color proportions will be 100% from 0 to 100%. So basically what happens is you start at y equals 0 and then you have to go up all the way to the point of whatever the proportion of white is. So let's say that white is 10%, well then you go up to y equals 10. Okay, so then from there, so then you make a rectangle that is white, and that is from y equals 10, or y equals 0 to y equals 10, and from 0 to 1, based on x start. And then to draw the second one, we have a loop. We have a loop here, and it basically says, okay, so we grab the upper bound of the last color we looked at, and we make that the lower bound for the next color, and then we make the upper bound just the proportion of the new color plus the proportion of the old color. So here's what I'm saying. Let's pretend that white is 10 again, and that red, dark red, is 13. Okay. So then we have to draw the white line from y equals 0 to y equals 10, but then we have to draw the dark red one from y equals 10 all the way to y equals 23. 13 plus 10 equals 23 because we need to represent 13% of dark red. And it does that for every single color until it reaches the top at, obviously at black. And yeah, so obviously not every single color that we have will be represented in every single image, but it's pretty close and it's pretty good, I think so. Yeah, I think it's pretty good. And yeah, so this sets the y-axis to 0 to 100 and x limit to 0 to 10. And that's mainly for the videos. So you'll see in the video that I show, what happens is that the plot is pretty large for, it's basically the size of this when we draw the color lines right next to each other. And what we want is we want it to fill up the plot. So some of the lines are sort of thick, and some of them are thin based on how many frames there are, but obviously we can't fit 700. If there's 700 frames, we can't fit 700 of these lines in one figure. So we sort of have to scale it down. But instead of changing the width, we just extend the plot out. I know that's a little bit confusing without being able to see what it means, but basically it ensures that no matter how many frames we have, we will always be able to have we will always be able to place all of the color lines within the plot, even if they're super thin. And then we just turn off the axis to make it look nice, because otherwise you'd see like the Y, it just wouldn't look good. So we just turn the axis off. Okay, so then we come back here and we get the 3D cluster and the 3D manipulation cluster, and they're basically the same thing, just obviously for, one's for the regular and one's for the manipulated. And those look like this. So I know it's a little bit of a cluster, but basically what happens is that for every single 1%, for every single percent of a color that you have, there will be 1 pixel on here. So say that you have, and it rounds up too. So say that you have 5% green, then there will be 5 greens on here. There will be 5 green dots. If you have 100% black, there will be 100. And they're all outlined with black, except for black, of course, because it's outlined with white just to make it, more visible and everything. And yeah, these are pretty cool. Obviously with 32 colors, it's a little bit difficult to really plot it so it looks really nice, but it's, you can kind of see the individual ones. It's easier to see with the manipulated one because there's less colors. And yeah, I think the 3D cluster looks pretty nice. We can mess around with it if we want to. I was thinking of just making it spin around every so often because it would look cool. And yeah, so how do we actually make this? Well, first of all, you have to give it the data, you have to give it the proportions, a title, you have to send the color values over so that you're actually able to change the colors of the dots. That's just sort of a given at this point. That's really important. And obviously you label the X, Y, and Z axes. And so here's where this is probably the most confusing part. You have to create 32 clusters, right? There's 32 clusters because there's 32 colors. And what you do is you create a random X, a random Y, and a random Z based on a center, which is changed by this +10, this +10, and if you can see, it's like it goes to -20 and plus. And there's I have a whole system here so that they don't overlap too much, although it's really hard with 32 colors to not have them overlap. And it essentially creates these random XYZ points, and it creates them based on the proportion. It rounds it. So say you have 0.7 white, well, it will create one dot that has a random X, a random Y, and a random Z, all centered around this central point because it's uniformly distributed. I know that's confusing. The reason why this isn't in a loop as well is because MATLAB, you can't have an array in a single element of another array, which is kind of ridiculous to me. So we had to do these manually, which was awful. And then this actually plots them. So this generates the clusters, this generates the coordinates, and the scatter 3 actually plots them onto the plot, or the scatter plot. And this just changes the color based on the color values that we already went over, and this changes the outline to black and all that. It changes the size to 20. It's pretty easy stuff. It's pretty easy to change as well, which is nice. And yeah, so I actually forgot to go over the graph interface. This is really simple. It's your data, title, color values, plot. Basically, all graphs need an X label and a Y label. They need a plot to actually put something on. They need, at least in our case, they need the color values, they need a title, and they need the data, which in this case is the proportions. And obviously they need a method to create the graph. I mean, how else are you supposed to do it if you how else are you supposed to make a graph if you don't have a create graph method? And it's also important to note that while this is technically an interface, MATLAB doesn't actually have interfaces. This is more like just an abstract superclass, but it's really, like, its job is just as an interface, and it's actually kind of nice because that way we don't have to keep on repeating variables, and it just sort of sets up a nice little starting point for graphs, especially if we want to make one in the future. So now this is probably, actually, I know I said other lines are the most important lines, but this right here from 83 to 87 is probably the most important if statement you'll ever see in your life. So why is it important? Well, basically, if it's the first frame that you're looking at, this is why the first frame equals true statement is so important. Then what happens is it creates these figures. It physically creates the figure and it generates it. But if it's not the first frame, which it won't be after you run through this code because it's set to false, then what happens? It just updates the subplots. And this is where you choose which figure you want to do, and it just updates the subplots from there. It doesn't generate a new figure. So the first time I did this, I was sort of, an idiot, and I just generated a figure every single frame that I went through, and it crashed my computer, and I had to restart my computer. Luckily, everything was mostly like saved, which reminds me to save. But yeah, you don't want to do that. You don't want to create a figure for every single frame. You just want to update it, and it actually looks pretty cool when it's updating with the videos. And this is actually where everything is drawn onto the figure. I already went through the drawing process, like putting things on everything. I just did it out of order. Like everything is like the math's all there, and everything's technically where it's supposed to be, but it's not actually graphed yet onto the figure until the very end. Now this is also important. So if it is a video, this is what determines, this is what allows you to skip frames. So if it's a video, you can skip frames with this for loop. So if it's 1 to 1, obviously you're only going to step up once to the next frame, so you're not skipping any frames. However, if you go 1 to 10, then you go to the next, you go to the frame that is 10 steps ahead of you. And that way you skip the other 9 frames, which is pretty nice because MATLAB's really slow in doing this. And it also increases the frame count, which is important because if the frame count is greater than the total number of frames, then basically the video should just, like, the video should stop, because at that point, like, the video ended. If we're at a point where we apparently went through more frames than the video has, so that at that point we stop looking at the video object, and that just sort of makes things more efficient. And that's really all of the code. That's really all of it. I'll show you right now. Obviously this is a test class, like this isn't the official code. Like it's basically a copy of the official code, but in case I just like messed around with anything here, I didn't want to save it for obvious reasons. But these figures normally aren't showed, and I'll actually show you how the close all does this. The close all just gets rid of every single figure, which is really cool. But this is what it normally looks like when we run an image. So it gives you the bar graphs, and then it gives you this, and the color variation line is a little bit thick, but we can change it. And yeah, that's that's really what it does for images. However, what's really cool about this is that we can do it for videos. So if we do sample video .mp4 for example, and then let's just do it like the first few frames. Let's just do it with a frame by frame, because this is I think it's skip. Yeah, there it is. Skippable. We'll make this one. I think it's 739 frames total, and I'm not kidding you. It might take like 2.5 to 3 hours to get through every single one. So we're not gonna do that. We're gonna skip some frames, but I kind of want to show you what it looks like frame by frame at first. It's really kind of cool how everything works and everything sort of changes. Like all these bar graphs update. It's kind of hard to see like frame by frame, but yeah, like here's the here it is. Like it's going frame by frame, as you can see, frame 4, frame 5, and it changes the 3D cluster graph. Obviously the color variation lines are plotted directly next to each other every single time, which is pretty cool. And it's like exact, so this will end up filling up all the way to over here, but we're not gonna see that because we're not gonna stay up until 6 in the morning, even though it's already 4:22. But yeah, so you can see how sort of the original image and the manipulated image sort of vary a little bit, which is, it's sort of cool. It's really not that big of a deal, but it's pretty cool. And you can see the green for the grass, and the black for the I guess for the dude emerging, and for everything. And again, I might change the way that gray works a little bit. I might make it a little less strict, because I was trying to make it really strict because I was wondering why there was so much gray appearing. But now I sort of know, like, okay, it's cool, like everything's working now, so I can sort of shift the gray back to normal standards, probably like less than 5 or 10 each or something like that. And yeah, so this is how it looks frame by frame, and it's sort of cool. We can get another video if we want. This one's a little bit boring at first. And it's kind of hard to see, but the bar graphs are also updating every time. It's kind of hard to see frame by frame. I'll change it so that it isn't only frame by frame, and my kitty is underneath me. She's so cute. But yeah, so I'll change it so that we can skip frames. So it's I can never find the skippable frame. I honestly. Find that. There it is. Okay, let's do every 25. This is still gonna go kind of slow, but it's 25 times faster, right? Okay, so here's where we can really see the change, especially in the bar graph, but not only the bar graph, but this. So as you can see, the color variation line is a little bit thicker so that it takes up the whole plot. Can sort of see how it's changing. I kind of want to see how this is changing as well, because I just want to prove that it is. There's a point here where there's like a huge jump where the sky appears, and yeah, like you can see it changing over here a little bit. And yeah, it's kind of cool when the sky appears. Yeah, see, look, it turns really blue. Like you can sort of see where where different sort of camera cuts are and everything. And and it's funny because the manipulated image is just all black. It's basically just all black. Yeah, I think this is a pretty nice step in the right direction, even though the color line isn't perfect by any means. It does its job. I think it's pretty accurate in regards to what colors are actually where, and all that good stuff. But there's always room for change, and we can do more colors, maybe. I don't know about that, but yeah. So this is the this is pretty cool. I think it's pretty cool, at least. I don't know. Yeah. So it's going on, and it's about to get to the end. You can see the butterfly come in, and yeah. So that's that. And only thing I can complain about here is the butterfly. I think it should be a little bit, there should be more pink rather than it being just it not being pink. I don't know why it's not pink. That's the really only thing that I saw that was a little bit off, was the pink not really being there. I mean, it's sort of there. You can sort of see it. If we zoom in, well, there, pink right there. There's sort of some pink, but not enough. There's not enough pink. So that might be an issue, a small issue that I can change like right now. Yeah, that's pretty much all there is to it. I think, we're pretty good for right now. As long as we mess around with the colors a little bit, we get the Arduinos working. I think this could be like a pretty legitimate project. Obviously, I'm going to mess around with stuff. I'm going to make the code a lot more neater. I'm going to make it so that these 3D images can spin around. I'm probably going to make a different figure for the frame so that you can just see them better. I don't know. I think it'll look nice, guys. So I'll see you guys later, okay? Sorry for taking up 55 minutes of your time. I'll see you guys. Peace.